This is the screencast for section 5.1, example 4, simplifying by expanding and using identities, trigonometric expressions. In example 4, it wants us to simplify the expression, and I'm going to rewrite that because that looks really messy to me. The secant of x plus 1 times secant of x minus 1 all over sine squared of x. Now, I see in the numerator here that I have a difference of squares. And if you remember from Algebra 1 and Algebra 2, a squared minus b squared factors into be a minus b times a plus b. So in this situation here, we do have a difference of squares. A is secant, b is 1. So when I multiply those back together, I will get secant squared of x minus 1 squared, which is 1, over the sine squared of x. Now that numerator looks familiar to me. I see a secant squared and a 1, but that's not really the Pythagorean identity. The Pythagorean identity says 1 plus tangent squared of x equals secant squared of x. But that identity can be altered to work with what I need here. If I subtract 1 from both sides, I get tangent squared of x equals secant squared of x minus 1, exactly what I have in the numerator. So I'm going to rewrite that numerator to say tangent squared of x over sine squared of x. Now, if you remember from example 3, one of our strategies is to change everything to sines and cosines. So the numerator, tangent squared of x, is going to be sine squared of x divided by cosine squared of x. So that expression, which means tangent squared, is still going to be divided by the sine squared of x. Well, now I can take the numerator, and instead of dividing by the denominator, I will multiply by the reciprocal. So I'll have sine squared of x over cosine squared of x. Now instead of divided by sine squared, I'm going to multiply by 1 over sine squared of x. So the sine squared of x cancels out, and I have 1 over cosine squared, which is in fact secant squared of x. The now try problem, number 25, says simplify the expression to either a constant, so a number, or a basic trig function, so sine, cosine, tangent, secant, cosecant, cotangent. Support your result graphically. So let's see here, 25. Secant squared plus cosecant squared doesn't sound familiar to me. It doesn't sound like a trig identity. I mean, I see trig squared, but that just doesn't sound right. Minus tangent squared and cotangent squared. See, my Pythagorean identities don't have secant and cosecant in them, or tangent and cotangent. I know that there's a Pythagorean identity that has tangent and secant, and there's another one that's got cotangent and cosecant. So I'm going to actually distribute this negative sign and rewrite. So let's see. Secant squared x plus cosecant squared x minus tangent squared x minus cotangent squared x. So there is a Pythagorean identity that has secant squared and tangent squared in it. So I'm going to write those two next to each other. Secant squared x minus tangent squared x. Then plus cosecant squared x. And then I know I have another Pythagorean identity that will have cotangent squared x. Now, similar to how I've shown you to alter Pythagorean identities, I'm going to take 1 plus tangent squared x equals secant squared x. I need this to be secant squared minus tangent squared, but look at this. If I subtract tangent squared x from both sides, I get 1 equals secant squared x minus tangent squared x. So far, this expression right here is 1. Plus, now let's see what happens over here. The Pythagorean identity starts out as cotangent squared of x plus 1 equals cosecant squared of x. Well, if I subtract cotangent squared of x from both sides, I get 1 equals cosecant, messy, cosecant squared of x minus cotangent squared of x. So this expression here equals 1. So my answer is 2. This whole mess up here simplifies down to just 2.